Hello everybody. My name is Thomas Dietler. I'm from the Zurich office and I would ask you kindly to mute all your microphones so we don't be disturbed by noise from outside. Today we will talk about geological investigations for an alternative flood protection measures in a project in Switzerland. The agenda will be as follows. First, I will show you the location where the project is in Switzerland. Then the background to this project. Why do we study this? Then third, what are the alternatives for the flood protection measures? What is the initial knowledge and the critical points from the geological point of view? And what site investigations were planned and executed? And finally, the geological interpretation out of it and the conclusions. I think this theme, this topic, is not only interesting for the geologists among us, but also for all hydropower engineers, as this problem we face here can be experienced in every hydropower project we are dealing with. So the project location is in the very northwest of Switzerland, south of the city of Basel. The location is a small village called Grellingen, and it is on the river Birs, which is a contributory to the river Rhine, which passes through Basel. The hydropower scheme we are talking about is the Büttenen run-of-river project, and partly we are also dealing with the upstream scheme called Moos. You see the circle in this area. So the background is a flood event in summer 2007. You see on the left picture the cave or height the scheme Moos, which is upstream of Grellingen, and there we had an overtopping of the right abutment, the right structures, with a severe erosion of the right bank, right abutment of this small hydropower plant. Further downstream in the village, close to the river, several houses were flooded, as shown in this picture in the middle. And on the other side of the river, it looked at that time like this. It was estimated that it was more than a HQ 100, meaning more than 350 cubic meters per second flood. It is not a huge flood compared to large rivers, but for this small Birs River, it is quite a lot of water. We have one alternative for the flood protection measure, which is elaborated by a local consulting company, and this alternative comprises traditional measures like higher diversion walls, higher dams along the river to protect the gardens and the places on both sides. However, the owners of the houses and their inhabitants do not like this idea. because it will change their quite idyllic situations they have nowadays. Furthermore, the actual hazard maps also indicate that flood will arrive from the hillside, and of course will be captured in this area, which should actually be protected from the flood from riverside. So we have not an optimal solution at the moment, and that's why the authorities, together with the owner of the river plant here, were thinking about the alternative hydropower measure. This looks like here, you see. This is the weir, existing weir on a quite high bedrock ridge. It is many decades old, and the idea is to lower the weir sill by about 1.70 meters, meaning from elevation 314 to an elevation of 312.5 meters above sea level, as you can see on the right side picture. To save costs, actually the idea is only to rebuild one half of this two-fold or two-sector weir. The idea further is to, with this lowering of the weir sill, to flush sediments deposited in the reservoir out of the area to produce or to give more retention volume during a flood. There are several critical points for the feasibility of this alternative too. First is, of course, the morphology of the bedrock surface in the reservoir area, which has an impact on the ability of sediment flushing. As you can see on this picture, the surface is quite heterogeneous and irregular due to bedrock erosion by the river. The bedrock is a limestone of Jurassic period. Secondly, what are the properties of the deposited sediments in the reservoir, which has also an impact on the ability of sediment flushing. This photograph is taken through the water, that's why it is not so clear, but we will come back to this later. Thirdly, what are the properties of the reservoir banks? Are they stable or not? Especially as we need for the sediment flushing a quick drawdown of the reservoir, and then these banks, river banks with the houses on both sides, might become unstable. And lastly, but not least, we have an alluvial area to the south of the reservoir, which we don't know the hydrogeological conditions in this area. Why we have to give the geological investigations quite a heavy part in this project. As mentioned earlier, the morphology of the bedrock surface is quite heterogeneous with pods, dips and ridges. So this will have quite a high input on the influence on the flushing of the reservoir, the sediments. The sediments are coarse-grained and fines from our upstream contributory, And the reservoir banks, they are protected by a various of different walls and measures, which itself are in different states of quality. I will not go further in detail in this topic. And what will be a main topic of this speech is the situation in the alluvial plain. From old boreholes and from bedrock outcrops, we found that there is an old prehistoric river course with a deep bedrock valley south of the current river flow. This we have to investigate in more detail. The investigation program consists of two phases. The first phase we executed late in winter, early spring this time, with the investigations of the reservoir area. For this purpose, we hired a boat which is usually working on the River Rhine in Basel to execute bathymetric with sonic echo sounders to map the sediment surface in the reservoir, and we wanted also to map and get information about the bedrock surface underneath these sediments. The first investigation with the bathymetry was quite successful, and we received a highly precise and detailed map of the sediment surface in the reservoir area. The processing of this raw data was done by the owner of the boat, and we see clearly the typical Talweg with the deep sections in dark blue and the more higher areas with the accumulation of sediments in orange and red. Here on the right-hand side, the weir is located. Here is the alluvial plain, and here is the road bridge. These are the cornerstones of the next slides. However, the results from the sediment sounding failed. We have obtained only multiples from the sediment surface. Why this? Why didn't we see anything from the bedrock surface? Probably the source from the boat was too weak. The sediments deposited in the reservoir too compact, and that's why we could not find out where is the bedrock surface. These raw data were actually processed by our colleagues from AFRY Vienna. The second phase of investigations was on the land, on this alluvial plain to the south of the reservoir. And it is three topics. First, geological survey, then investigations by two boreholes, and groundwater monitoring. The geophysical survey on land was executed in August with 3 hybrid seismic lines as indicated on this map. The 2 yellow stars are the locations originally planned for the 2 boreholes. Just based on the initial knowledge from the old boreholes, I placed them in this area. However, after having received the results from the geophysical survey, I moved the 2 locations to the blue stars. This borehole here is now drilled just yesterday we completed it, and this borehole has now started. The groundwater monitoring will be executed by a local consulting company from practical reasons, and it should last at least 1 year. Here, one example, the results from the line 3 of the hybrid seismic survey. The hybrid seismic survey is a combination of the refraction seismic, as you see on this picture, where we get the seismic P wave velocities of the rocks, and the reflection seismic. Here you see the hybrid, the combination of both, and last, on the right side, the interpretation, geological interpretation of the results. This is the borehole, the old borehole from 1965, which first indicated this deep valley. The first results from the boreholes now, for the new boreholes, you see on the left side. On the top layer, which is about 3,50 meters thick, we have the topsoil and artificial fillings, and below this inert artificial filling, an old waste deposit with coals and other human artifacts. We have to closer investigate this later. Underneath, the alluvial deposits start with a clayey silt, which is quite dense and has a low water permeability. And the main part of the alluvial deposits is built up by silty gravel with sand and a varying amount of clay. And of course, rounded cobbles, pebbles and boulders. The bedrock surface we reached in a depth of 22.7 meters, and we stopped the borehole yesterday evening at 24 meters. It is now interesting how the second borehole, you see on the right side, will look like when it's finished. Do we find this old waste deposit as well? And will the bedrock surface occur where we assume it will be based on the geophysical survey? And another interesting issue is the reservoir level is at 316 meters above sea level, and the groundwater within the alluvial deposits is deeper at around 310 meters above sea level. Based on this geophysical information and also later from the boreholes, I improved the contour lines of the bedrock surface, and it looks now like that. The purple or pink shaded area is below 300 meters above sea level, which is quite clearly deeper than the area of today's river course. Based on this contour line, I constructed 5 cross sections. And you see here the cross section 1 is at the weir, and the information from the old borehole from 1965. The borehole, the section 2 and 3, where the 2 new boreholes lie in between, we see this situation here with the groundwater level deeper than the reservoir. It is quite impressive how deep this valley is reaching, and the river today is running on the left part. Here you see a contour line map of the thickness of the deposited sediments above the bedrock surface. In the deepest area, we have more than 30 meters sediments. And in the area of the reservoir, in this, just downstream of the bridge, we have around 20 to 25 meters. And this decreases to maybe 5 to 0 meter sediments close to the weir. Later, I constructed, based on these different results, longitudinal sections along the reservoir. In green, you see the bedrock surface with the left bank, the center line, and the right bank. In brown, the same for the left, center, and the right side, the level of the sediments in the reservoir. The blue area represents all sediments which lie above the new wire seal with the elevation 312.5 meters. And this will be the interesting area regarding possible flushing of sediments. As a conclusion, we can say the following. A rough estimation of the sediment in the reservoir lying above 312.5 meters sea level is around 11,000 cubic meters. This sediment volume between the weir and the road bridge is expected to be flushed with a drawdown or during a flood. The next steps are, I have to adjust with the latest results from the borehole all the contour line maps, but as I see from the first borehole, it is not much to be adjusted. The geophysics is quite correct. Then we have to reassess the feasibility of the alternative 2 with the reconstruction of the weir, especially concerning the hydrogeological situation at the right side, this alluvial plain. And of course, the stability of the river, of the reservoir banks with the houses on top. Then, if we have finished our report, it is up to the authority and the scheme owner to decide which alternative shall be applied for this flood protection project. Okay, this was a short introduction to this interesting project, and please, I'm open for questions. Hello?
Good afternoon. Could we just go back to your slide on the contours of the ancient riverbed?
This one?
Yeah, so on the right-hand side, what's the existing river level? I mean, it looks as though it's kind of a rocky bed.
Yeah, you see,
Right at the edge there.
on the current river course, which goes like this, we have bedrock outcrops on a level of 310 meters above sea level, meaning the river level here is just below. It is a difference between the reservoir, which is 316, and 310 or 309 plus some centimeters of almost 6 meters, or of a little bit more than 6 meters. And in this borehole, for example, here, which is from 1965, the bedrock surface is at a level of 295.9 meters. And this is also from, this borehole is also from 1965. The level is, the bedrock surface level is again 1 meter deeper. And then here, meaning it is deeper than what we can see today further upstream.
Yeah, but even so, it's kind of surprising that such a level of silt is built up in that old channel.
Yeah, no, for me, actually, it's not anymore surprising. It is now the second project I work with where we found such a hidden prehistoric valley. We assume that in prehistoric time, further downstream, there happened something like a big landslide or something like this, which impounded the river, and the area behind this slope failure was slowly filled up by the river with alluvial material, and then at a certain point when the river could run over the natural dam further downstream, he was searching, or he was eroding a new riverbed, and this is what we see today.
That makes sense.
In another example, further closer to the Swiss Alps, we found a valley which was actually eroded before the glacier arrived, and then the glacier arrived a second time and produced a glacier lake, which was slowly filled up with clay. And the river, in meantime, was eroding quite another different course. So it is actually more often to find such hidden river valleys than you assume. Other questions?
Yes, hi, Thomas Gulli speaking.
Hi.
Many thanks for your presentation. I have a question, maybe not that related to the geological topic, but if you flush sediments, you might have undesired ecological effects downstream.
Yeah.
What is the reason to choose to flush the sediments instead to remove the sediments in the reservoir? Thank you.
This is difficult to remove the sediments from the reservoir just because of the dimensions we have. The reservoir is quite narrow, and it is probably much more expensive than flushing, and there is also problems, you see, with the main idea is to lower the sediment surface, that we get more retention volume into the depths and not into the height. and the weir needs some refurbishment, and though it is the idea to make it that we can flush now and then or when it's required. Another negative impact of the digging or the excavating the sediments without flushing is actually then you have to be very careful not to go under this certain level, because then we might destabilize the banks, the river banks. With the flushing, we stay on a certain level which is not critical for the stability of the river banks.
It's me again, Gordon Newton. I worked on the Rosiris Dam raising a few years ago, which is on the Blue Nile River, and there were 5 10-meter high, 10-meter wide gates at a very low level in the riverbed, whose intention was to flush silt.
Yeah.
And that had been in operation since the 1960s. And they had found that even though they were operating these gates every single year, keeping them open for 1 or 2 months, the flow of sort of 15,000 cubic meters per second through them, the slope of the silt upstream of these gates was in the region of 30 degrees,
Yeah.
which is pretty steep.
Yeah.
And the quantity of silt flushed was very minimal.
Yeah, I know, we know this problem from other projects. The prerequisite to flush out the sediments on a larger extent is a complete drawdown.
Yeah.
Then you can erode, flush out the material sedimented in the reservoir much better than only when you do not the drawdown, complete drawdown. Then you have this quite steep cone, which is located very close to the opening.
Which will then erode back up the reservoir, yes.
Yeah. We are fully aware of this problem, and this will be one of the next steps by my colleague Reno Zünd, who has to check this again. It was now the task was to get more information about the geological conditions. Where is the bedrock surface? Is there a ridge behind the existing weir which will obstruct flushing, for example? And what are the hydrogeological conditions in these alluvial deposits? Do we run into some problems? But at the moment, due to this quite fine-grained top layer of the alluvials, I think we are quite happy that the water from the reservoir is not severely interacting with the groundwater in the alluvials.
Okay, everybody, I'm sorry to interrupt, but time is up, about 5 minutes. So we need to say thank you so much, Thomas, for your presentation.
Welcome. Thank you for the participants.
Yeah, thank you very much.
Thank you. Okay, bye-bye.
Thank you very much, Thomas. Bye-bye.
Thank you.
You're welcome. Bye-bye.
Vielen Dank, Thomas.
Bitte.
Sehr gut gemacht. Danke.
Okay.
Thank you, Thomas.